Hopefully you are seeing an image taken in Tanzania in 2019, last year. This is exploding dots. I'm so delighted to be here to share this with one and all, and thank you for coming along. This has become a worldwide phenomenon, which I just cannot believe. It's all grassroots, all volunteers. It's just curriculum mathematics that's just literally exploded across the entire planet. At this point, over 6 million students and their fabulous teachers have played with the story of place value and computational thinking, going through primary school maths, going through middle school maths, going through high school maths, going to college level maths and beyond. Some unsolved research problems still baffling mathematicians to this day. So I'm absolutely thrilled to be sharing this story with you. I need to point out, hopefully you're seeing everything on screen, and you can see it's live, you can see my fingers moving around. I'm actually an extraordinarily boring fellow. Everything I'm going to do today is actually available on this website, g'daymath.com/courses. G'day, because I'm Australian, so it's like saying, hello kitty, so it's g'day math. G'daymath.com courses, and there you'll find exploding dots, everything I'll cover today, and so much more. So in fact, you don't even need me for the next hour. In fact, you can just like close off right now and go and enjoy all the videos and all the text that's there available right now. But my other point is, if you do stay for the hour, which would be fabulous if you did, don't bother trying to take notes. Just have an experience for the hour, take it in the moment. And then if you want to take in what really happened so in a whirlwind way for this past hour, you've always got this resource, g'daymath.com courses, to find exploding dots again and take it in slowly at pace. All right, so let's begin. Let's just no further ado. Let me share with you this wondrous story of exploding dots that seem to have swept the globe. Here goes. It all begins with a story that's not true. So when I was a child, I invented a machine, and all the machine was a row of boxes. Let's go as far to the left as you desire. None of this is true. The idea of this machine is that you put dots in this machine, but I also gave it a very strange name because I made a little rule for myself, which I described as a 2-1 machine, which I wrote in a funny backwards way because I was a young child and I just knew no different. I just called it a 2-1 machine. Great, but the idea is dots go into this machine. So if I put in 1 dot, the idea is that dots will always go into the rightmost box. Here it comes, 1 dot, zoom. And it's not very exciting. 1 dot, I'm afraid, just stays as 1 dot. Put in a second dot. Here comes dot number 2, always the rightmost box. Let's make that a colon. Always the rightmost box. Here it comes, zoom. And then something exciting happens because whenever there are 2 dots in a box, they explode and disappear, kaboom, and are replaced by 1 dot, 1 place to the left. 2 dots became 1 dot, hence the name 2-1 machine. Okay, grand. So now I've got this strange setup for the number 2. It's no dots, no dots, no dots, no dots, no dots, 1 dot, 0 dots. I'm not going to bother writing all the leading zeros, but I will write 1, 0 as this mysterious code for the number 2 in a 2-1 machine. Now I'm going to put in a third dot. Here comes dot number 3. Always the rightmost box, zoom. Well, nothing very exciting, but right now I've got nothing, 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 1, 1. So the code for 3 is 1, 1. I have a feeling putting in a 4th dot is going to be particularly exciting. Here it comes, always the rightmost box, zoom. 2 dots, explode, kaboom! And 1 dot, 1 place to the left. 2 dots again, kaboom! Replaced with 1 dot, 1 place to the left. So 4 has the code, nothing, 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 1, 0, 0. 1, 0, 0. This is loads of fun, I'm gonna do it again. Put in 5, put in a 5th dot. Before I do it, can you see in your mind's eye, the code is gonna be 1, 0, 1. Here it comes, the 5th dot, zoom. There it is, 1, 0, 1. Can you see in the mind's eye what the 2-1 machine code is going to be for a 6th dot? What happens if I put a 6th dot in the machine? What's the code going to be? All right, I'm about to do it. Can you see it in your mind's eye? Here it comes, the 6th dot, rightmost box, zoom. 2 dots in the box explode, kaboom. 1 place to the left, 1, 1, 0. Grand. Okay, let's have some fun. 13. What's the code for the number 13 in a 2-1 machine? Now, I don't see the chat, so I've got to figure out how to re-share my screen so I can see the chat. But what I'm going to ask you to do, if you want to try it, purely optional, type what you think the answer is in the chat, but don't press enter yet. I'm going to ask us all press enter at the same time, as soon as I figure out how to see the chat at the same time as I'm presenting. So if you can figure out the code, just write it in, what you think it is, but don't press enter just yet. I'm going to see if I can see the chat for myself. Expand this, can I do that? No. Well, I'm going to stop sharing for a moment while I figure this out. One moment, please. Chat. All right, when you're ready, everyone press enter right now. Oh, lots of different answers. I see 1101, lots of those. I saw 111, I saw 101, 1, I saw 11010. I'm seeing that one a lot. Okay, all right, okay. That's what people are saying, it seems, but we're all over the place, which is great. Oh, I saw this one, 10001. Okay, great. Let me share my screen again. Oh, I have to bounce back and forth on this. Where's my camera? It's that one, there it is, the visualizer. Off we go. All right, lots of different answers. So that was the most popular answer, but I saw that answer. And I will tell you, it's very annoying to me because I skipped the numbers 7, 8, 9, 10, 11, and 12. And I think some people are on to me, but here's my honest answer to this. To me, right now, this is hard. I was surprised no one wrote that in the chat. You're allowed to write the word too hard in the chat sometimes. But 13 seems to be the most popular answer, but there are other contenders. So I don't know which one it's going to be. And here's my idea. I'm just going to move on. Because I had a flash of insight one day. After playing with the machine codes of the 2-1 machine for hours and hours on end, because they were just jolly fun, I had this realization that instead of doing a 2-1 machine, I could also do a 3-1 machine. Whoa. Now, obviously, the idea here is that 3 dots now explode to become 1. So let's just do it. Put in 1 dot, not very exciting, 1 dot. Put in a second dot, again, not very exciting, still 2 dots. However, put in the third dot, always the rightmost box. There it is, 3 dots, kaboom! Let's explode, 1 dot, 1 place to the left. The code for 3 is now 1, 0. Put in a fourth dot, here it comes, the rightmost box, zoom, 1, 1. Put in the fifth dot, the rightmost box, zoom, 1, 2. Can you see in your mind's eye what the code for 6 is going to be in a 3-1 machine? Here it comes, zoom, kaboom, dot. 2, 0. All right, let me juggle around with bouncing around this time on the chat, but can you type into chat, don't press enter just yet, what you think the code for the number 13 might be, just make a guess, or if it's too hard, just say too hard. Who likes hard work? Not many people. So give it a go and I will unshare and look at the chat. And when we say go, I will say press enter. So press enter on the word go right now. Oh, lots of answers. 111s, 1101s, 101s. Oh, lots of 111s. Lots of, so I have a feeling some people are on to me. Some people know what these machines are, but I'm still a young child here in this untrue story. Oh, 112, that's a good one. Some 2s. Yes, it's possible to get some 2s in these codes, of course. Well, that's a good question. Could you ever get a 3 in this code? Could you ever get a 4 in this code? If you think about it for a while, no. If you had 3 in a box, you'd explode them away. So you won't see the number 3. And you won't see the number 4 because you had 4 in a box. 3 of those would explode away, and so on. All right, so I'm going to go back to showing my screen. There's the visualizer. Great. So it seems like 111 was the most popular answer, but still my personal favorite answer is hard. Okay. Hours of fun in this untrue story. I don't know why I'm doing this as a young child. I'm just doing it for the fun of it. I like looking at codes in 2-1 machines and 3-1 machines. But then I had another realization. Instead of doing a 2-1 machine or a 3-1 machine, I could go wild and crazy and do a 4-1 machine or a 5-1 machine. Or let me go particularly mad. Let's go all the way up to a 10-1 machine. 10-1 machine. Whoa, crazy. In fact, let's go particularly crazy. I'm going to put in 273 dots in a 10-1 machine. Let's go absolutely wild. We have 50 minutes left together. I have plenty of time to actually do it. I'm going to do it on the screen right now. I'm going to put in 273 dots. Here they come. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 18, 19, 20, 21. Okay, so that's getting close, getting up to 273. I can't see you, but if you want to yell to me on the chat, stop. I won't see the chat, but just say, stop, that's enough, this is boring, this is dreary. Is that close enough? Okay, sure, that's close enough to 273 dots. Okay, we'll stop there. All right, 273 dots. So let's see if I can just think my way through this one this time. So my first question is, yes, no question. Will there be any explosions? Why, yes, there's lots of 10s amongst those 273 dots that explode. Question number 2, how many explosions will there be? You think through this, there's 263 dots in there. So, oh, okay, there's lots of groups of 10s. There's actually 27 groups of 10. So there'll be 27 explosions. All right, 27 explosions. Kaboom, kapow, kazing, kazoop, kazoop, kadip, kaboop, galoop, galip, all explosions. Any dots left behind? Well, it's 273 dots. There'll be 3 dots left behind. So let me do that. So there'll be 3 dots, lots of explosions. Kaboom, kapow, kazing, kazoop, kazoop. And there'll be 3 dots left behind. 1, 2, 3. Hope it's clear enough. And okay, I'm getting bored of drawing dots. Can I just write each explosion makes a dot? 27 explosions makes 27 dots in that box. Is it okay if we just write the number 27 this time? I hope so. All right, okay. Now, moving on. Any more explosions? Well, yeah, there's 2 groups of 10 in there, and 7 dots will be left behind. So 2 more explosions. Kaboom, dot, kapow, dot. And that will leave 7 dots behind. 4, 5, 6, 7. So now I can see that the secret code for 273 in a 10-run machine is 2 dots, 7 dots, 3 dots. 273 is 273. Whoa, whoa. So obviously something is going on in these machines. The code for 273 is the same digits, 273. Now I can't see you right now, unfortunately, but of course we just want to know right now, what are these machines actually doing? So let's see if we can figure that out. In fact, let me go back to the beginning. This 2-1 machine. Let's see if I can give this away. See if I can make sense of what's happening here. Well, let me take that paper out from underneath. All right, so we said dots here were worth 1. So a dot there is worth 1. 1 dot, 1 dot, always 1 dot, except 2 of these, 2 1s, exploded, kaboom, and made a dot over here. So this dot must be worth 2 1s. It must be worth 2 1s, which is 2. And 2 of these dots, 2 2s, kaboom, made one of those dots. So this dot here must be worth 2 2s, 4. And 2 of these made one of those. This must be worth 2 4s, 8. And 2 of these makes one of those, 16. And 2 of them make one of these, 32. And 2 of these make one of those, 64. And 2 of them make 128, one of those, and so on and so on and so on. We're seeing all the doubling numbers here because this machine is basically doubling the dots as we go along. And if you look, 6 we said was 1, 1, 0. 1 of those, and 0 of those. And look, 1, 4, and 1, 2, and no 1s does indeed make 6. So now look at all these contended answers for the number 13. That was the most popular one. Is that correct? Was it 1, 1, 0, 1? Actually, can you see, and I mean literally see, that that is the correct code for 13? 1, 8, 1, 4, no 2s, and 1, 1 indeed doth 13 make. Wow, you can literally see it. Welcome to base 2. We're discovering base 2 numbers, place value in the powers of 2. Wow, people call this binary, and there it is, right before our very eyes. In this untrue story, as a young child, I've just discovered binary numbers. In which case, I bet I know what's going on with the 3-1 machine. Dots here are worth 1. 3 of these make one of those, kaboom. So this is worth 3 1s. 3 1s is 3. 3 of these makes one of those, kaboom. 3 3s is 9. 3 of these makes one of those, 27. 3 of those makes one of them, 81. 3 of these make one of those, 243. 3 of these makes one of the next one, 729, and I find it too hard, I'll stop there. Bingo. Now on the chat, 111 was the biggest contender for the number 13. One of those, one of those, one of those. And I can't see you, but can you see that that is correct? Literally see it's correct. One of those, one of those, one of those, 1 9, 1 3, 1 1, indeed is 13. Wow, I can cross out that word now. I found a way to make it simple for my simple brain. Lovely. And of course, the 10-1 machine, our favorite, must be working the same way. Dots here worth 1. 10 of these makes one of those. 10 of these makes one of those. 10 10s is 100. 10 hundreds is 1,000. 10,000, and so on. Beautiful. Welcome to base 10. And in fact, this is the base value that we as a society have chosen to use. In fact, if I write out the number 273 in words, 273. Actually, I don't know what there's a big contention in the US. People are not allowed to write the word and anymore in there. Is that happening in the UK? 200, I'll write it because I like the word and 73. Anyhow, however you choose to write it, 273, it is literally saying 2 hundreds. because it's literally 200s. There they are. And 7t. That ty is short in English for 10, a little shorthand for 10. It's saying 7 tens. And look, it really is 7 tens, and it's 3. And it's 3 ones. There it is. We, in this society, speak 10-1 machine. We work in base 10. Now, I have a question, though. That begs the question, why base 10? Why are we humans obsessed with the number 10 on matters of arithmetic and counting? And if you think about it for a while, because we humans are equipped with these things. Ooh, 10 of them, in fact. We see our hands, we got our digits, our fingers, we count on these things all the time. So it seems very natural to us humans to think 10 is a very natural number for counting. In fact, we even call these individual things digits, and we call these individual things digits. Not a coincidence. Digits, the same word. Though I have to say, there are some cultures that didn't go base 10. There are some cultures that went base 20 instead. In fact, what makes you think some cultures might go base 20? What was they think was the natural thing to count on? Well, these are probably very clever people that thought they could use their toes as well. They probably used fingers and toes. Now, I live in the US now, grew up in Australia, as you can tell from the name G'day, G'dayMath.com. But in Australia, in the US, there's a very famous speech by Abraham Lincoln, the Gettysburg Address, which begins 4 score and 7 years ago. It's interesting, Abe Lincoln was speaking a little bit of base 20 right there. 4 score, the word score is an old word for 20. So 4 score and 7 years ago is literally 4 20s and 7, 87 years ago. So we have vestiges of base 20 still to this day. In fact, if you speak French, how do you say 87 au français? I don't speak French. If you think about it, something like 87, which literally word for word is 4 20s and 7. So even in French, there's a little bit of base 20. Actually, some cultures went base 12. Base 12. Now, historians aren't clear why they did that, but there's one theory out there, which is this one. Many people realize there's a very natural way to count to 12 on one hand. In fact, you'll see in many parts of India and Southeast Asia today, people still do this. You've got 4 long fingers, each naturally divided into 3 sections, and you've got a natural point of the thumb. And some people count this way on a hand. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12. In fact, 12 is a very natural way to count on one hand, so maybe that's why we have base 12 in some cultures. In fact, 12 is a really good number for weights and measures and trade issues. For example, how many items are in a dozen? That we do this today. Why, it's 12. How many inches are in a foot? Why, it's 12. How many hours are in a day? And I mean literally a day. When the very first clocks were sundials that only worked during daylight, in which case they say, well, let's divide the number of parts of a day into 12. There are 12 hours in a day. And then when we started measuring time at night as well, we said, well, let's just do another 12 hours for the night. And that's why we say there's 24 hours a day, but it's really based on the number 12 again. And 12 is a really handy number in everyday life, because in trade and working in markets and so forth, you often want common fractions of things, like half of things, a third or a quarter. Half of a dozen is nice, it's 6. A third of a dozen is nice, it's 4. A quarter of a dozen is nice, it's 3. 10 is actually very awkward for the basic fractions. Sure, half of 10 is nice, it's 5. But a quarter of a 10 is not nice, and a third of 10 is really not nice. So in everyday life, 12 is a very good number to use. Great. All right, so we humans thought 12 or thought 10, if we're thinking this way. We thought 20, we went fingers or toes. We may have thought 12 because of this. But that's not, that's unique to our humanness. I happen to know that Martians only have 4 fingers on 2 hands, in which case on Mars, they'd say 8 is the way to go. They probably use base 8. Anyhow, I'm rambling on. We only have 40 more minutes together, and what I want to do in these 40 minutes is go through the entire kindergarten to high school curriculum in the exploding dots viewpoint and show how everything is straightforward if you think about dots in this exploding way. So what I want to do now is go through all of primary school and middle school mathematics and high school mathematics in one astounding hit. All right, so in which case, I will follow society's convention and work base 10. We seem to be living in a Western society that loves base 10. From now on, we will now do a 10-1 machine. All right, so let's whip through primary school maths. Here goes, speed, experience. What's the first thing you do? Once you've learned how to write numbers, what's the first real mathematical thing you do? Most people say it's addition. So let's do some addition right now together for a few minutes. All right, so example, what's 231 plus 438? All right, well, that's pretty easy. It's just, what, 6, 6, 9, is that right? Great. Were your eyes on the screen right at that moment? Did you see what I did? I went 2 plus 4 is 6, 3 plus 3 is 6, 1 plus 8 is 9. I went left to right. Now, what were you trained to do when doing long addition? I bet you were trained to go right to left. All right, so now here's a true part of the story. When I was a child, I thought it was very strange that I was being taught to read left to right in every class except mathematics. In mathematics, then we go right to left, right to left. And I said to myself, well, what's the big difference? I mean, if I go left to right here, I get 669. If I go right to left, I get 669. Either way, it's the same. What's the big deal? Well, I know what's in your mind. I chose the example that was way too nice. All right, so let's choose a juicy example. Let's choose 279 plus, I don't know, 142. Bingo. All right, 2 plus 1 is 3, 7 plus 4 is 11, 9 plus 2 is 11. The answer is 311. 311. In fact, I'm going to prove to you I'm right. That might sound strange, but here's a 10-1 machine. This is asking for 270, 7 tens and 9, there it is. And it's saying, please add 1 more 100. No worries, 1 more 100. Please add 4 more 10s. Piece of cake, 4 more 10s. Please add 2 1s. I can so do that. And what do I have? I literally have 3 300s. I literally have 11 10s. I have 11 1s. The answer is 311. I'm even saying it correctly. 311. Oh, sorry, 311. Well, wasn't saying correctly, but now I am. Whoa. Now, society does not like 11. Does not like saying 11. Though I will tell you, society is just being fickle there. In Old English, they did have words for 11 and 12. 11 tens and 12 tens were actually valid words. It's just in this modern times, we think 11 is silly. You can't say 11. Okay, there's nothing mathematically wrong with this answer, but the question now is, how can I fix this up for society, which seems to be so fickle and demanding? It won't let me say 11 and it won't let me say 11 for once. And the answer is, well, I can do some explosions. 10 explode to become 1 after all. So let's do some explosions. Sure. Question, do you want to explode the 11 or the 11? Okay, let's do the 11. Now, most people go right to left. I'm going to break that mold. I'm going to explode 10 dots from here. So 10 dots explode, kaboom. That's hard for me to do this on paper, but there's 1 dot left behind, an extra dot there. So the answer is 401T11. 401T11. I'm even saying that correctly. Okay, it still sounds very strange to society's ears. Let's do another explosion. 10 here explode, kaboom, leaving 1 behind. 1 dot left behind, extra dot there. The answer is 402T1. 402T1. Now, I will argue we should be saying 2T, but we don't. We want people to say 20 because English is so weird and hard. 421, 402T1, there it is. And of course, what we were all taught and what we do teach in the standard algorithm is, of course, correct. Going from right to left, you say 9 plus 2 is 11, but you say, no, don't write 11. Do an explosion right away. 10 explode, leaving 1 behind and an extra dot amongst the 10s. I think people call that carrying. Is that called carrying? I don't even know what the jargon is. Okay, exploding. This one is what, 12? You don't write 12. No, don't write 12. Just write 2 and do an extra explosion. And 4. So actually, the standard algorithm is exactly the same as my method. It says go right to left and do the explosions as you go along. Sure, I personally and honestly like to go left to right, as I was taught to read, and do the explosions at the end. It's just a style thing. It's all good. It's all grand. All right, in this whirlwind tour of all of education, let's keep going. Addition. Once you've done addition, what's the next thing? Ooh, most people say subtraction, but that's too hard. No, I'm not going to do subtraction. Subtraction is too hard. I don't like hard work. How about 2783? Let's do multiplication times 4. Times 4. Okay. In the chat, don't press enter. What do you think is the James Tanton 3-second answer to this problem? How do you think I'm going to answer this problem right now when I like to avoid hard work and don't worry about what society thinks of me as I do it? Okay, I'm going to stop sharing my screen so I can see the chat for a moment. Type in an answer, and then when you're ready, enter it now. Hard, I like hard, too hard. I like it, all this is good. Woo! Double. Oh, double, yep, double. I know what people say about double. Sounds like a turkey, that's all good. Oh, I love it. Love it. Okay, let me share the answers I saw whipping by that you've seen as well. Share, there we go. All right, many people guessed what I'm going to do. Here's how my brain's thinking. You know, I'm not going to always draw dots and boxes in every single time because I can see it in my mind. This is asking for 2,000s, 700s, 8 10s, and 3 1s, and please quadruple everything. Okay, surely I can quadruple everything. Quadruple 2 is 8. Quadruple 7 is 28. It's hard part. So instead of having 2,000, now have 8,000. Instead of having 700s, now have 2,800s. Quadruple this is 32. Instead of having 8 10s, I now have 32 10s. Instead of having 3 1s, I now have 12 1s. So the answer is 8,000, 2,800, 32t, 12. Whoa, whoa. 8,000, 2,800, 32t, 12. And I'm saying it correctly. Now, society doesn't like that answer. As a professional mathematician, I stand by that answer 100%. There's nothing wrong with it. It's mathematically solid, mathematically correct. It's just society thinks it's weird. So, next challenge. How could we fix that answer for society's sake? Not for math's sake, for society's sake. What could we do? All right, well, I might just give you a little moment to think about that, 30 seconds, literally 30 seconds, but I'll give away the answer because I'm having trouble seeing chats as well, as you know. But think about it for 30 seconds, and then I'll reveal how my brain works on this. All right, here's my brain. Obviously, there are going to be some explosions. There's lots of 10s in there. There's lots of 10s in there. And there's a 10 in there as well. So we have to do some explosions. I'm going to do them in any old random order because that's the mood I'm in right now. Example, 3 10s in here. 3 groups of 10 explode. Boom, leave 2 behind, an extra 3 dots there. That makes 31. So the answer is 8,000, 3,100, 2t12. Great. That still sounds weird to society. Let's keep going. Maybe 3 explode in here, leaving 1 behind, extra 3 dots there. So the answer is now 11,102 t12. That's great. Maybe 10 explode from here, 2 behind, extra dot there makes 3. Maybe the answer is 11,132. Or maybe I should say 3t2, but English is weird. We want to say 30 instead. Gosh, English is hard. Okay, great. Technically, I can do another explosion here, leave 1 dot behind, an extra dot there in the 10,000. So the answer is 110,000, 1,132. And English is actually inconsistent. It's totally inconsistent. There's actually, I don't know how we teach this to young kids because it's so confusing. But even my very original answer, when I say 32t, people think I'm weird. If I said 2,800, which I did, it doesn't actually sound weird to our ears. So society will let me say 2,800, but it won't let me say 32t. I can't explain why, it's just society. Also, this 11,000, we actually do prefer to say 11,000 rather than 110,000, 1,000. We actually say 11,000. So society wants to say 11,000s and not make me do explosions. Good luck. I do not know how we teach this because the math is straightforward. It's just societal conventions are really horrific and really confusing and really hard. Oh, okay, good enough for multiplication because we're going to whip through this entire K through 12 experience. Okay, I was naughty. I did actually skip over subtraction. I should do subtraction. All right, subtraction. Let me do it. Naughty James. Let's do it. The reason I skip over subtraction is because I actually do not believe subtraction exists. There is no such thing as a subtraction. To me, subtraction is the addition of the opposite. Subtraction is the addition of the opposite. Okay, because that now puts me in a pickle. Because so far, I've been talking about these things, which I've been calling dots. Now I need the notion of the opposite of a dot, something that's opposite of that, because I want to add opposites now. For the sake of ease, let me just draw an open circle to be the opposite. But here's my big question. What do you want me to call the opposite of a dot? Do you have a clever name for the opposite of a dot? If I just type it into the chat, because I'll stop my screen sharing so I can look at the chat. What would you like me to call the opposite of a dot? What's a good name for that? Okay. Whole, Todd, undot. Oh, antidot. Don't. Negative, antidot. All right. Lots of good names. Okay. Let me share my screen again so I can write some of these down. This is awesome. So I'm seeing antidot. I'm seeing undot. I'm seeing Todd. I'm seeing opdot. I'm seeing other negative dot. I'm seeing whole because it looks like a whole. Lots of things. Brilliant. Okay. obviously, since you know me, and I've actually given this presentation, or versions of this presentation all around the globe, it is astounding to me when I'm doing this in front of a live audience that I can see and interact with. The audience is primarily adults. Adults tend to choose this word. But no matter where I am in the world, students, whatever age, even if English is their second language, tell me Todd. And I need to explain Todd because I love how kids' minds work. It's actually the word dot backwards. I saw a lot of Todds in that chat. Let me just go with Todd to honor kids and their brilliant thinking. All right, so an anti-dot, the opposite of a dot is a Todd. And I'll do an open circle for that or a hole. And the idea is that if you take a dot and you add to it a Todd, they undo each other, they annihilate, they go poof, they just disappear. I won't say explode, they go poof and disappear and leave me nothing. Literally, that's the picture I see. That is the correct picture. They leave me nothing. For example, here's what I meant. I don't believe in subtraction. For example, if I had to work out 5, take away 3, to me it's really 5 plus 3 Todds, the opposite of 3. And I can see, oh, annihilation, poof, annihilation, poof, annihilation, poof, leaving me 2 actual dots, 2. So to me, subtraction is the addition of the opposite. I know it's in the effect that sort of took things away, but actually it's still addition, which I love. Because here's how I think about school arithmetic. Let's do a subtraction problem, like 276 take away 154. And let me draw the actual picture of this. Let me go through the laborious work of drawing dots and Todds. We're in a 10-1 machine. I've got 2 hundreds. I've got 7 tens. I've got 6 ones, 276. There we go. Please add 1 anti-100. Sure, 1 Todd. Please add 5 anti-10s. No worries, 5 anti-10s. Please add 4 anti-1s. Piece of cake, 4 anti-1s. And what's going to happen? Will there be some annihilations? Yes. Poof. Hard to do this on paper, but I'm going to do it. 5 of them. Poof, 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 poof. Is that 5? And then 4. Poof, 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 poof. Annihilate. And I'm left with 1, 2, 2. It's as though I went left to right. 2 take away 1 is 1. 7 take away 5 is 2. 6 take away 4 is 2. Left to right again. You've got to love it. Left to right is the way to go. Every class, left to right, even maths class. Whoa. But I know what you're probably screaming at me. That was too easy. That was too nice. Let's do a really awkward one. How about say 224 take away 157? That's juicier. That's much juicier. Let's do that one. All right, 324. Please add 1 anti-100, 5 anti-10s, and 7 anti-1s. All right, what happens? Annihilations? You bet. Poof, 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 poof. And what am I left with? 2, -3, -3. 2 actual hundreds, 3 anti-10s, 3 anti-1s. The answer is 200, -3t, -3. Mathematically solid, mathematically correct, fabulous. 2, -3, -3. Beautiful, love it. 3 take away 1 is 2, 2 take away 5 is -3, 4 take away 7 is -3. 200, -3t, -3. I have no problem with that. As a mathematician, professional mathematician even, I give that my stamp of approval. Yes, well done. But society doesn't like it. Society so doesn't like that. So now we have a quandary. How are we going to fix up this weird answer for society's sake? It's mathematically good, but society doesn't accept it. What could we do? And this is actually a lovely moment in teaching right now because that's a question for this class. What can we possibly do? It's really about teaching problem solving and the confidence to think your way through things. Obviously, if I only want the answer 324 minus 157, my goal would be get out a calculator. If that's my goal is to get the answer, don't do any of this. But really, it's an opportunity to teach thinking, teach 21st century thinking in this old 1800s model of what we teach kids. I love it. Now, what can we do? Now, if we were live, I'd ask you to chime up, but let me just sort of give it away. You might be thinking we could take one of these dots here and unexplode it because it really came from 10 dots over here because we need extra dots in this spot to do some annihilation. So let me do some unexploding. Now, the key thing is we've got to come up with a cool sound effect for unexploding. What am I going to do? I'll go, what am I going to do? I'll do it. Okay, a lot of people do a sucking sound. I'll do a sucking sound. So that 1 dot there was really 10 dots over yonder. 4, 5, 6, 7, 8, 9, 10. Well, they're really gone. So great. So now I've got 1 of these and an extra 10 dots there. But then there's now some annihilations. Poof, 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 poof. So that's really leaving 7 dots there. 170, -3. Love it. That's getting closer. But now I can unexplode again. Do this one and make 10 here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there's one less dot there. So that's 6 there. And I've added an extra 10 dots there. But then again, 3 more annihilations. Poof, 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 leaving 7 here. 167. The answer is 167. There it is. And society, I think, will like that answer. Actually, do you know what? I really like this method of going just left to right. 3 taken 1 is 2. 2 taken 5 is -3. 4 taken 7 is -3. Because actually, can you see that this is that answer? Because what's that 2 really? It's really 200. What's that first -3 really? Well, it's really -30. And what's that second -3? Well, it's really just -3. 3 ones, 3 anti-ones. Can you see that that is actually 167? Whoa. So actually, maybe you really should just go left to right and then just see what the answer is from that. Gotta love it. All right, okay, speeding along. Here we are. We've got 23 minutes left together. And we've done what? Addition, subtraction, a little bit of multiplication. Now comes the big one, division. Let's do division. Actually, before I do that, let me just point out one thing that's really nice. Let me go back to a simple example like 1, 3, 0, 2. And if I multiply that by 3, let me literally draw that picture. Let me literally draw that picture. What I'm saying here, in a 10-1 machine, that's 1,000, 300s, 0 10s, and 2 1s. Please triple everything. Well, okay, I can say, okay, well, I'll take this dot and I'll now triple it. I can take this dot and now triple it, and this dot and triple it, and this dot and triple it. And I take this dot and triple it, and this dot and triple it. So actually what I did is I tripled that dot, I tripled that dot, that dot, that dot, that dot, and that dot. If I gave the answer 3096 and say find groups of 3 in it, I would draw a picture like this. There's 3906. There's groups of 3. And in fact, I see one group of 3 at this level. I see 3 groups of 3 at that level. And I see 2 groups of 3 at this level. I say, oh, there must be 1 group of 3 at the thousands, 3 at the hundreds, none at the tens, and 2 at the ones level. This must be 1302. So actually, I can see from my picture where answers to multiplication problems must have come from. That is, I can start doing division. Whoa, whoa. Okay, so this is a speed experience. Let me give you a hard one right off the bat. I assume we're just going to be pros at this, and I'm just going to go straight for the hard one. Let's do something juicy like 276 divided by 12. So this is literally asking for how many 12s could I see in a picture of 276? Now, one really tedious but philosophically correct way you could do it is go ahead and draw 276 dots. Here's 276 things. Oh, I'm doing it again. Okay, close enough, 276. And just say, okay, I need to find groups of 12. And go, okay, there's a group of 12, 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 and 4 hours later, I'll find some groups of 12. Okay, that's one way we did that. You could do that. I don't recommend it, but it's actually correct. Then, for me, back in Australia, year 5 for me, we were taught something really strange working this out. So I'm going to share with you the algorithm I was taught some 40 years ago, way back in another continent in Australia, which went like this. As young kids, we were told to do this. Write a very funny symbol. Okay. Write the big number under the symbol and write the smaller number to the left of the symbol. Okay. Very strange, very strange. All right, now it gets worse. I'm now telling a true story. So I had been trained at that point in every class up to year 5 that every class reads left to right except maths. Maths goes right to left. Except all of a sudden we're told, no, just do this one from left to right, as though it was normal. That was shocker number 1 for me. I've got about 5 shockers on this. I struggled with this as a 10-year-old. That suddenly we just changed direction. You trained me for 5 years to always go right to left in maths, and now we're just suddenly going left to right. Then we're told, okay, going left to right, look at the number 2 and say, how many times does 12 go into 2? You say, don't be silly, it doesn't go to 2 at all. Then we said, look at 2, 7, 27. Shocker number 2 for me. I said to myself as a kid, hang on, the number's not 27 and a 6, the number's 276. You can't pull out parts of numbers and just call it 27. That was bizarre to me. However, I grew up in a very, very strict system that wanted me to just memorize and do, so I obeyed. I was a very good, obedient child as a student. You say, okay, how many times does 12 go into 27? It goes in twice. Here's the scary part. Then you had to write the number 2 at the top, and apparently alignment mattered. I think that's what it is. Then in Australia, we had to actually write 2 times 12 is 24. Okay, sure, why not? Then here comes bizarreness number 3. Then you just do a subtraction problem. Why not? 27 take away 24 is 3. That is weird. Why are we doing subtraction in the middle of this? Okay, so I've got weirdness 1, 2, and 3 so far. Here comes the kicker, weirdness number 4. This one really threw me for a loop as a kid, though I never questioned it because I was taught to obey. Okay, we got the answer 3. 27 take 24 is 3. Then we had to draw little arrows, bring the 6 down, and this 3 just magically changes to 36. It's back to being a bigger number again. Weird, weird. Then we're told as kids, ask how many times 12 go into 36? It goes in 3 times. And then you write 36 again, do another subtraction problem. Why not? And you get 0, and apparently getting 0 is good. And apparently the answer is 23. And in fact, if you do this, if you actually find how many groups of 12 in a picture of 26, you'll find there are 23 groups of them. Whoa, whoa. You have to admit, this is bizarre and strange and as weird as beans. Though I don't know if beans are weird. Anyhow, they're as weird as weird beans. Okay. So right now, I'd like to take a moment of therapy for my 10-year-old self. Can we figure out what's really going on in this mighty strange algorithm that I was taught 40 years ago, and I know many curricula still teach today? Now, I know I'm a bit harsh because I'm a lot of curricula. I've now broken this down and done partial subtraction things, all good stuff. Don't get me wrong. But in the end, we still teach this algorithm, and I want personal help for my 10-year-old self. So 276 divided by 12. All right, so I'm going to draw a picture of 276, but I'm going to draw a more sophisticated picture. I'll draw a 10-1 machine picture of 276. It's 276. There it is. And I'm looking for 12. What does 12 look like? Now, when I was drawing groups of 12, I was literally drawing groups of 12 like this. But I've got to be careful, because in a 10-1 machine, groups of 12 have a little explosion. Kaboom, I actually get 10 explode, leaving 2 behind and 1 dot, 1 place over. But the point is, my 12 dots are really all sitting here in this rightmost box, and a kaboom spilled 1 over. All right, so 12 dots in the rightmost box. So there's a picture of 276. Here's a picture of 12. I'm looking for 1 dot next to 2 dots, and I'm realizing all 12 dots are really in the right part of that picture. Now the question is, can I find any 12s, any of this picture of 12, in 276, this picture of 276? And you stare at it for a while and say, what, golly gee, yes, loads of them. For example, there's 1 dot next to 2 dots. There's 1 dot next to 2 dots, just like that. And in fact, I realized, oh, there must have been 12 dots here, and kaboom, 1 spilled over. So there's actually one group of 12 right at that level, right there, kaboom, spillage. In fact, I see another group of 12 at that level. There must have been 12 dots right there, kaboom, spilled over. So there's really 12 dots right there. I don't see any more 1 dots next to 2 dots right there. Oh, but I do over here, 1 dot next to 2 dots. My loops are getting a bit weird. Because actually, there's 12 dots here, but it went kaboom, spilled over. There's one group at that level. There's another one at that level. 12 dots here, kaboom, spilled over. Oh, look, and my loop's now getting mighty weird. But there's a third loop, 12 dots right here, kaboom, spilled over. Actually, I see this is a picture of 12 dots, 2 at the tens level, 3 at the ones level. The answer must be 23. Whoa, whoa. And just so we can complete the picture, of course, what I was taught 40 years ago is not incorrect. It's actually doing the same thing. Now, I do have a hard time with it, or except that, well, no, I don't have a hard time with it. Everything I do in maths is left to right. When you're asked to look at 2, you look at these 2 dots. When we're asked to look at 27, we're asked to look at these 2 dots and these 7 dots. I will personally still object to calling it 27. What we're really being asked to do is just say, look at the 2 dots and 7 dots. Do you see any 12s there? And the answer is yes, we saw 2 of them. And we even wrote, I've got running out of room here, we saw 2 of them at that level. We wrote a 2 at the top here. I even wrote a 2 at the top there. We're in good sync. Or maybe that fits. Oh, I can do that. That fits on the screen. All right, bingo. Then we said, since did a subtraction problem, take away 24 and 3. Well, what's that 3? Well, that 3 makes sense. It's actually those 3 dots still left over to be dealt with. Ah, now I know what subtraction is doing. It's saying there's still 3 more dots to deal with. Okay, we'll deal with them. What we're going to do now, this weird 6, bring it down, and 3 just magically change to 36. No, don't call it 36. It's not the right thing to do. What you're really doing is saying now, focusing your attention on the next 6 dots, these 3 dots and these 6 dots. And we saw 3 more groups of 12. We wrote 3. We saw 3 more groups of 12. We wrote 3. The subtraction says, bingo, done. There's no more dots left over to deal with. Beautiful, beautiful. In fact, even if there was an extra dot here, if I was doing, say, 277 divided by 12, I'd see, oh, there's one dot left over. So I'd say, oh, I can see remainders. The answer would be 23, remainder 1, or 1 dot still waiting to divide by 12, 23 and 1/12. Wow, there it is, division. Bingo. All right, so there, in that speed experience with 14 minutes to go, I've whipped us all the way through, grades, years 6, 7, somewhere up around there. All right, I should get to high school maths. Let's do high school maths. All right, here's the magical thing. Everything I just did right today does not care about us being human. It doesn't care about the fact that we have 10 digits and think that 10 is the neatest thing to do arithmetic with. Everything we did would work in binary, base 2. In fact, computers do everything we did today as though they just had 2 fingers. You've got electrical switches that are either on or off. It's like having 2 fingers. It's 2 symbols, zeros and ones. Or you could do it in Martian, base 8. Everything we did today would work in Martian just fine. In fact, I want to prove that everything we did today will work in any base you like by repeating what we just did in all bases all at once. Here's how I'm going to do it. I'm going to draw you a machine, and I'm not going to tell you what the machine is. You're not going to know. It could be a 10-1 machine. I'm not going to tell you. It could be a 3-1 machine. I am just not going to tell you. It could be a 7-1 machine. You just won't know because I'm just not going to tell you. It's the mood I'm in right now. All right, but I will give a nod to algebra curricula across the globe, because if you don't know a certain value, people seem to be obsessed with a particular letter of the alphabet over and over again if you don't know it. So that letter is X. Thank you to Rene Descartes. We're obsessed with the letter X if we don't know a number. So I will call this an X1 machine as a nod to algebra curriculum. But I'm not telling you what X is in my brain. It could be 10. I could be thinking X equals 10, which case is a 10-1 machine. I could be thinking X equals 2, this is a 2-1 machine. I'm just not going to tell you what value of X I have in my mind. So you know nothing about this machine. You know nothing about this machine, other than it's just an X1 machine, and Tanton is not telling you what X is. Well, actually, that's not true. You do know some basic things. You know that dots here are always worth 1, because that's the game I'm playing. 1 dot there is worth 1. And you know that X of these makes 1 of those. Well, X group of 1s would be worth X. And you know that X of these, X's, X groups of X, is X's. That's X times X. That's X squared. And you know, X of these, XX squareds makes 1 of those. XX squareds is X cubed. And you know, XX cubes is 1 of those, X to the 4th, and so on. So you do know these values of dots in these boxes. In fact, if I told you that X really was 10 in my brain all along, are these the correct numbers for a 10-1 machine? 1, yes. 10, yes. 10 squared is 100. That's what we had before. Yep. 10 cubed is 1,000. That's what we had before. Yep. 10 to the 4th is 10,000. Bingo. This could be a 10-1 machine if X is 10. 2-1 machine, the very first machine I did today. If X is 2, is this correct for a 2-1 machine? 1, 2. 2 squared is 4. 2 cubed is 8. 2 to the 4th is 16. 1, 2, 4, 8, 16. Yep, they're the numbers I first wrote today. All right, so this now does indeed represent all possible machines all at once. Whoa, whoa. Okay, we just did a grade 5, a year 5 long division problem, at least back in my curriculum back in Australia 40 years ago. No warning, no lead-in, no nothing. I want us right now to work out 2x squared plus 7x plus 6 divided by x plus 2. Let's now do a high school algebra problem. Let's divide this quadratic expression, this, I don't know what they call it, trinomials or something, by that thing. I don't know what they call it. Whatever it is. I want you to divide that by that. I will give us 30 seconds for you to have a feeling of panic. I'd like you to sit with a feeling of panic for 30 seconds, and then we'll figure our way through this. Meanwhile, I'll check out the chat because I see there's 67 messages in chat. I wonder what you're saying. Let me find out. Oh, you're saying nice things to each other. Thank you. A lot of people are thinking it better than apples and oranges. Thank you. I like apples and I like oranges. All right, all right. So this is crazy. By the way, high school teachers are probably objecting to the fact that I haven't put parentheses around these things, but I've actually used this horizontal bar. That's called a vinculum. A vinculum was an old way that people actually did group things. So actually I'm mathematically correct. There's a vinculum, say I want all this thing divided by all that thing. All right, so this is another wonderful opportunity, how to turn our curriculum into an opportunity to teach 21st century thinking and confidence. I've given us something that's scary and emotionally scary. Step number 1 in problem solving, being your honest human self and having a human reaction. Right now, my reaction is scared. I have no idea what to do. I'm feeling panicky. Bingo. That is honestly step one to solve problem solving. And people never talk about that. Be human, have an emotional reaction. Step two, do what I just did. Take a deep breath and do something, anything. So the question is, can we do anything here? Now, this is my greatest wish upon the world, our future generations. If we just teach the world, when faced with a challenge and a problem that seems scary, to just do something, anything, just take a step forward. That might be forward, it might not be forward. Just take a step. That'll be the greatest gift for our future generation. And mathematics is actually a perfect vehicle for teaching that. Right now, there's something as scary and horrible like this. Why are we doing this? Not because I need to divide this. If I really need to divide this, I'll go to Wolfram Alpha personally. I would go to software. We are citizens of the 21st century. So it's not about getting the answer. It's about this teaching what it means to move forward when faced with a challenge. All right, so can we do something? I bet most people are thinking, at least we can draw this. I can draw 2x squareds. I can draw 7x's. And I can draw 6 1s. I can at least draw this thing. But I can even draw x plus 2. That would look like this. 1 dot next to 2 dots, I guess. 1x and 2 1s. So now the question is, can I find any 1 dot next to 2 dots in that picture up there? Oh, that's a division problem. I can do that. There's 1 dot next to 2 dots. Great, 1 at that level. There's 1 dot next to 2 dots. Super, another 1 at that level. There's another 1 dot next to 2 dots. My lip's getting a bit weird. There's another 1 at that level, 1 dot next to 2 dots. In fact, here's another one. My lip's getting extra weird now. There we go. Whoa, whoa, I've done something. In fact, I even see what it is. I found 2 copies of this at the x level and 3 copies of this at the 1's level. Oh, the answer must be 2x plus 3. 2 at the x level, 3 at the 1's level. Whoa, whoa. Now here's the thing. I bet that felt like deja vu. Have we done this already? And if you stare at that picture and you stare at my grade 5 picture, how am I going to do this? I'm going to flip both pictures on the page at the same time. Can I do that? Look at that. Those pictures are identical. In fact, what if I revealed to you that x really was 10 all along in my brain? Then what have we actually done? This would be 2 10 squareds plus 7 10s plus 6. That would be the number 276 divided by 10 plus 2 by 12 apparently equals 23. 2 10s and 3, 23. Of course it is, because we did that. That's exactly what we did back in grade 5. High school polynomial division is a repeat of grade 5, and no one tells anyone that. Whoa, 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 whoa. Crazy. All right, I have 7 minutes left. I'm going to give you one to try all on your ownsies. Can you do this beast of a polynomial division completely on your own? X to the 4th plus 2x cubed plus 4x squared plus 6x plus 3, all divided by x squared plus 3. Watch out, x squared and no x's plus 3. Can you, in 1 minute, draw yourself a beautiful picture of that and work out the answer to that polynomial division problem? We were still great 5th graders here, but can you do it nonetheless? And by the way, this probably would be considered too hard in the US curriculum, because in the US curriculum, they only divide by linear terms. I'm making us divide by a quadratic term. But nonetheless, we can all do it. Give it a try. Okay. I'm going to whip through it right now because we have 5 minutes left together, and I'm going to see if I can get to a very important point in some speed. That space is annoying. Remember, we're looking for 1 dot blank 3 dots. 1 dot blank 3 dots. Does that work? You see that? So I guess all the dots are really here, and a lot of spillage occurred to go boom, 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 to get a dot way over there, but it's really all dots at that level. Beautiful. Now, that sort of loop is awkward. Can I get away with doing this? 1 dot blank 3 dots. Is that okay to do? 1 dot blank 3 dots. Okay, that's good. And then one more, because I see 1 dot blank 3 dots right there, and I see the answer is 1 at the x squared level, 2 at the x level, 1 at the x, and 1 at the units level. The answer must be x squared plus 2x plus 1. Amazing, amazing. Just draw a picture. Or at least draw a picture in your mind's eye. You'll love it. The trouble is, in 4 minutes, I have to tell you, we've got a serious problem. I think I've made this sound too nice. X cubed minus 3x plus 2 divided by x plus 2. What have I secretly been avoiding all this time? Tods, those anti-dots. Try this one, and you'll see we have a serious, serious problem. I've been feeling so good. I feel jazzed about being able to do all of high school arithmetic, polynomial algebra, but this one is a beast. 1x cubed, no x squareds, 3 anti-x's, and 2 1s. I'm looking for this. Oh, okay, x plus 2. I seem to be obsessed with 1 dot next to 2 dots. 1 dot next to 2 dots. Look at what I've got. X cubed minus 3x plus 2. Do you see any 1 dots next to 2 dots there? No. And I want to cry. So I guess this method actually doesn't work after all. So I have to sort of end on an anticlimax here. Oh, bother. Anything we can do? Anything we can do? Oh, people are chatting again. Okay, I'm afraid I don't want to fumble the chat because time is so tight now. We've got 3 minutes here to solve this crisis. We have a crisis. All right, one thought is, I could actually, if I want 1 dot next to 2 dots, try to bring these dots close together. It seems very appealing to unexplode this dot. And make a bunch of dots there. Brilliant idea, love that idea. Trouble is, it's an X1 machine. You don't know what X is. You don't know how many dots to draw here. Oh, so I can't unexplode. I can't unexplode. Oh, I really am stuck. My next emotional reaction, cry some more. All right, so it's not fun, but I'm about to give away a major, major flash of insight. When I do this with students, we get stuck and I wait for someone to actually come up with this idea. And the homework could be for my high school students is, tonight's homework is to go home and go for a 20-minute walk and just let your subconscious mull on what we could possibly do. That's it. That's my genuine homework. And invariably the next day, someone comes back with an idea. In fact, I love this problem because maths teaches a life lesson, a very important life lesson. Here's what it is. This is why I love being a maths teacher. This is why I love teaching polynomial division. Because right now is a major life skill. If there's something in life you want, make it happen and deal with the consequences. All right? I would love 2 dots to go with this 1 dot over here. It just seems I would love this to happen. So I'm going to say, if I want 1 dot next to 2 dots, make it happen. Beautiful. I made it happen. But I have to deal with the consequences because I can't just willy-nilly put in 2 dots in the box. This dot's meant to be empty. So how could I make this box still technically empty? And then you realize I could do that. Now, as a high school teacher, I know there's jargon there about like 0 pairs or something. Don't even use the jargon. Just do it. No naming. Just do it. Because I love this. Bingo. I found 1 dot next to 2 dots. Oh. Can I do it again? Yes. I want 1 dot to go here. Make it happen. Deal with the consequences. Beautiful. All right. Now, we've got about 30 seconds left. 1 at that level. Oh, now I feel I'm truly stuck. But then you realize, oh my goodness, look at this. Here's a complete anti-version of what I was looking for. Here's another anti-version of what I'm looking for. So actually, we did it in the end. The answer must be x squared minus 2x plus 1. Whoa, polynomial division, there we go. And this is just the beginning of the story. I've got us to high school polynomial algebra, but actually keep going. You can do infinite polynomials, get into infinite series. You can go into some weird things, get some unsolved research problems that's still baffling mathematicians today. Base X, get into fractional bases, get into negative bases, get into irrational bases, all by drawing pictures of dots and boxes. Math is a joyful pursuit of play, wonder, awe, and delight. So if you want to actually see the full story, here's that website again. I'll post it in the chat in just a moment when I stop sharing my screen, so you have it in the link there. Thank you for this very speedy experience. I guess you're about to go to your dinner time. I'm about to go have my morning brunch, and all is grand and good. So thank you for coming today. This has been a real joy, a real pleasure. And now I'm stopping sharing my screen, and I'll put that URL into the chat. Thank you, one and all.